Welcome back to The Explainer. Today we are jumping straight into what is arguably the ultimate bottleneck in the entire energy transition. We're talking advanced material science and battery engineering, specifically looking at that incredibly difficult journey of taking a brilliant idea from a highly controlled lab environment and turning it into a massive industrial-scale reality. If you're an industrial decision maker, an asset manager, or an engineer, you already know exactly how high the stakes are here. We're going to break down why this process is so notoriously difficult, and more importantly, how we can strategically bridge this massive gap.
Right off the bat, let's ask a pretty fundamental question. Why do battery breakthroughs that look absolutely perfect in a Nature paper completely bomb on the factory floor? I mean, think about it. We constantly see these incredible discoveries boasting exceptional theoretical capabilities, yet so many of them just never reach mass production. What is actually going wrong between that pristine, day-one scientific discovery and commercial reality?
Well, in the lab, you've got this hyper-controlled environment, right? It is essentially paper perfection. You're dealing with exceptional theoretical capabilities where everything works exactly as it was designed to. But try scaling that up to a gigafactory, and you collide headfirst with immense manufacturing variability and dynamic degradation. The sterile precision of the lab just completely shatters against the chaotic, highly variable reality of mass manufacturing. It's a stark contrast, and honestly, this disconnect is exactly where the vast majority of promising technologies crash and burn.
And this friction between the lab and the factory floor, it isn't just some minor hurdle. It is literally the ultimate bottleneck. For industrial decision makers and asset managers, this specific point of failure is the central problem in the whole energy transition. If we can't reliably take advanced battery tech from the lab and scale it up without catastrophic failure rates, the whole system just stalls out. It's the literal difference between a multi-million-dollar triumph and a massive, painful write-off.
So what actually creates this scaling valley of death? The data points to three structural walls: multi-scale dynamic degradation, contextual silos in R&D, and institutional inertia.
Let's unpack that first one, multi-scale dynamic degradation. Sounds like a mouthful, right? But think of it almost like metal rusting, just happening on a crazy microscopic level while a battery is constantly charging and discharging. It refers to the shifting degradation mechanisms that happen in materials at all sorts of various scales, from the tiny microscopic structure all the way up to the full battery system. And here is the absolute key for anyone managing energy storage assets. If you don't know exactly how that material breaks down under real-world factory stress, you simply cannot predict its financial value or lifespan.
And even brilliant material designs often fail because of the second barrier, contextual silos. Picture this, you've got a team of brilliant chemists, and they've designed an absolute masterpiece of a battery cell. But they aren't actually talking to the factory engineers who have to build the thing by the millions. They're totally isolated. Because these R&D teams are optimizing entirely for a sterile lab, they are oblivious to the chaos and variability of the factory floor. That lack of integration leads to massive friction the exact second the technology attempts to scale.
And that brings us to the third barrier, which honestly might be the hardest to shake: institutional inertia. A lot of institutions rely heavily on outdated, rigid validation processes, usually because they've got millions of dollars sunk into legacy testing equipment and long-standing protocols. These slow and flexible workflows simply cannot keep pace with the complex, rapid requirements of Gigafactory reality. It severely limits our ability to validate and scale true breakthroughs.
So we are definitely at a major crossroads here. On one side, we absolutely have to abandon the slow, siloed legacy validation workflows, the ones bogged down by that institutional inertia we just talked about. We need to evolve toward predictive multiphysics frameworks. We're talking about modern models that dynamically integrate data across all those different scales, ultimately resulting in the one thing we actually care about: predictable asset value. It's a necessary leap from old, failing methods to the integrated tools we actually need to bridge the gap.
Now, why does all this systemic theory actually matter on the ground? Well, it boils down to one incredibly painful business reality: reducing pilot line scrap rates. When new, totally untested material designs get shoved through those legacy workflows and hit the Gigafactory floor, manufacturing variability causes massive failure. The result? Unacceptably high pilot line scrap rates. It's an enormous, devastating waste of time, capital, and raw materials. Solving this bottleneck isn't just some abstract engineering challenge. It is an urgent financial imperative. The stakes are obviously huge here, but the good news? The roadmap forward is actually very clear. We need a strategic pivot to avoid the scrap heap. How should engineering teams evaluate new material designs to ensure they actually survive that jump from the lab to mass production. Our source data provides a definitive three-step criteria to make this pivot a reality.
These 3 strategic criteria are non-negotiable for industrial decision-makers. Step 1, you have to master multi-scale dynamic integration. That means breaking down those R&D silos to understand the material at every single structural level. Step 2, overcome manufacturing variability. You've got to plan for the chaos of the factory floor from day 1, not as an afterthought. And step 3, the ultimate goal, you must translate those unpredictable degradation mechanisms into bankable, predictable asset value.
And how do we actually pull off those 3 steps? The only truly robust way is by adopting predictive multi-physics frameworks. This means leaning on advanced computer simulations and fully integrated digital models, not just slow physical trial and error, to conquer that manufacturing variability. Relying on legacy validation is practically a guaranteed path to failure these days. But adopting these predictive digital frameworks, that is the definitive technological bridge over the scaling valley of death.
We've seen the massive gap between lab success and Gigafactory reality, and it's crystal clear that overcoming institutional inertia is absolutely mandatory. So I want to leave you with this provocative challenge directly from the source material to apply to your own day-to-day. How are your engineering or asset management teams tackling the friction between legacy validation workflows and predictive multiphysics frameworks? Are you stuck in the bottleneck, or are you actively building the bridge? Thanks so much for joining me for this explainer. I hope it helps you look at battery tech scale-up in a whole new light. Catch you next time.